Electrons I know are going to be traveling this way. I have an electric field that is traveling from the high potential to the low potential. I have an electric field basically traveling in the direction of current. So in this region right here, my electric field is traveling that way. Because there's no buildup of charge anywhere, that whatever charge I have flowing in one part of the wire is equal to the charge flowing in another part of the wire. A little bit of a hand wave here, but making the general case for the fact that the electric field throughout the wire is relatively constant. And I know if the electric field is constant, that delta V is equal to the electric field times, I did D before because that was the distance between the two plates, but I'm just going to use L here for the length of the wire. So E is just delta V divided by the length of the wire. So this becomes dropping my, you know what, I'm hand waving, so let's just make those go away. So Q delta V over LM. So what I've ended up with here is a general drift speed of my acceleration, Q delta V over LM times tau. Acceleration times time. Yes?
Just to clarify that, was that the same symbol that we used for torque?
Yes, it is. Yeah, the nice thing about point particles is there's no torque on a point particle by itself. So we can now take my current formula here, and that's going to be equal to Q times lowercase n capital A times Q delta V over L M tau. Now this is just generic at this point for whatever the particle is that's moving through. Let's actually be specific at this point and say it's an electron for what we're working with here. And so let's be specific to the electron. My Q here, I got two of them, I'm squaring it, is just E squared. If you're thinking, but electrons are negative, yeah, then I square it and it becomes positive. So I have E squared. This mass here would be the mass of the particle, which is the mass of the electron, so I'm going to stick that down here, so that's mass of the electron. And then I have N here, and tau. And then lastly, I'm left with A over L, delta V. And then I double check to make sure, because I'm writing it a little bit differently, I didn't leave anything else. And see, I got my Q's there. N, A, tau, delta V, L, and M. Okay.
What was the subscript by the M?
Sub E for mass of the electron.
Ah.
All right, let's think about what we have here. The first thing I have in parentheses, E squared over M sub E. This is specific to whatever the charge carrier is. It has nothing to do with the material itself. From our point of view, this first term right here is a constant once we recognize what the charge is, what object is actually moving to create the charge, an electron. So this is great, this is basically a constant. Now it doesn't have to be an electron if you get into the purity of it, but for practical purposes it is. N and tau, these are material specific. So whether I'm using aluminum, gold, silver, copper, that the charge carrier density, mobile charge carrier density, and the mean free path time, those would be specific to the material itself based upon density and where it is in the periodic table and so forth. A over L is wire specific. Not line specific, wire specific. And if you go to the hardware store to buy wire, thickness of wire, which will directly affect the area, and how much wire you're using definitely comes into effect. And then delta V is depending upon, well, what kind of power supply you're hooking it to. The first part there, E squared, little n tau over m sub E, this is known as the conductivity. And we are using a sigma yet one more time. We use the same thing for surface charge density. It's also used for conductivity. Now we don't do much with conductivity directly, but we do something with the reciprocal of it. 1 over the conductivity, and we're using the letter rho, and yes, we use the letter rho for density, but this is known as resistivity. And we do something with resistivity. If you ever get a question of what's the conductivity and I tell you the resistivity, just take the reciprocal. But this has reduced my equation over there to I is equal to rho A delta V over L. Now this is not the traditional form of it, so I'll put it in the traditional form. I'm going to solve for delta V. So delta V is equal to I L, oops, that rho is in the wrong place. There we go. It'd be sigma if it were on top, but it's the reciprocal, so rho is on the bottom. So IL rho over A. We got one more step. This right here. This, they gave a special name. Resistance. R is equal to rho L over A. This is resistance. It is not futile. Now recognize the physics involved here. Coulomb's law. That's it. Buried under all of this, the only physics involved is Coulomb's law. The rest is definitions. So far we've dealt with a mess of equations, but only one physics equation so far this semester. But this breaks down into that the voltage is equal to the current times the resistance. Or the potential difference is equal to current times resistance. This is Ohm's law. And that, fortunately, is really easily shown in a lab. However, we need to pause it there. May as well stop this. I'm going to hand some stuff back, unless you desperately have to run out of here.